Hey guys, this unit we're going to specifically talk about heat. We are going to talk about how heat transfers when you have things interacting, whether it's ice and hot cocoa or if it is burning a substance in order to create a chemical reaction. We're going to talk about how heat transfers, how it affects things, and how to solve for unknowns. So this unit's actually going to be broken down in a couple different pieces. The first one is going to be a simple equation. First, we have to define what heat is. Heat is a specific type of energy that is transferred between two objects due to a difference in temperature. Heat has a value of Q, which could be a capital Q or a lowercase q. It's measured in joules, just like all other forms of energy. Here's a note when it comes to thermal energy. There are two words that we could use to describe thermal energy. If it is contained within an object, it's called the internal energy. So for example, the energy of the molecules while they're moving, like solids being the awkward dude on the dance floor, liquids being ballroom dancing, and gases being a mosh pit. That's how you would describe the internal energy. When thermal energy is moving in between objects, it is considered or called heat. So that means as you sit on the stool during class, if you get up to leave for the next class period and somebody comes in and sits on your stool, if they feel the warmth on the stool, that's called heat because it moved from your body to the stool and then from the stool back into their body. So thermal energy could be called two things, internal energy or heat. And this energy is specific when it comes to the motion of the molecules inside the object. In addition to measuring the internal energy of an object, or the heat transfer between a hot object and a cold object, we can also pay attention to something called the specific heat capacity. The specific heat is defined as the amount of energy required to change the temperature of some mass of a substance by 1 degree Celsius. Specific heat is symbolized by lowercase c, and we are going to either solve for it or be given it in every single equation. Specific heat is special because it tells us how much energy is needed, and the lower the specific heat value is, the easier it is to change the temperature. The higher the specific heat value is, the harder it is to change the temperature. For example, water has a specific heat value of 4.18 kilojoules per kilogram degree Celsius. That means it takes 4.18 kilojoules of energy to raise water 1 degree Celsius. Now we can also write this as 4,180 joules per kilograms degree Celsius. All we have to pay attention to is what we want our final answer to be. A lot of times we'll use kilojoules just to make more reasonable numbers. So specific heat capacity is the amount of energy it takes to raise the temperature of a mass of substance 1 degree Celsius. Here's the specific heat formula. We would calculate the heat energy transferred, our Q value, by taking the specific heat of a substance, joules per kilogram degree Celsius, or kilojoules per kilogram degree Celsius, they are interchangeable, the mass of the substance in kilograms, and the delta T, or change in temperature. Now delta T is found by taking Tf minus Ti, the final minus the initial temperature. It could be positive or it could be negative based on whether we're gaining heat or losing heat. So this is our basic equation. We're going to do a simple example problem just using that basic equation before we introduce anything more difficult. How much heat energy is needed to raise the temperature of 1.8 kilograms of water from 10 degrees Celsius to 80 degrees Celsius? And again, I'm going to remind you what the specific heat of water is. It's 4,180 joules. So I'm going to list my knowns and unknowns. I have Q as my question mark, C equals 4,180, M is 1.8, and delta T is TF, which is 80, minus TI, which is 10, which is 70 degrees Celsius. And Q equals Cm delta T. Q equals 4,180 times 1.8 times 70. And this Q value is 500,026 680 joules. So that's a pretty big number. Our other option is we could take the same information and instead of using 4,180, we could use 4.18, and that would just change Q equals Cm delta T. Q equals 4.18 times 1.8 times 70, and Q would now be 526.68 kilojoules. So notice the numerical values are the same when we multiply those through. The difference is where our decimal place is. So this is just like converting from grams to kilograms. Joules to kilojoules is the same type of math. You just jump the decimal place 3 places to the left. So either are usable, they are interchangeable as long as your units match. So when you list your answer, you have to have kilojoules or joules listed specifically to match your numerical value. So this is a pretty easy example problem. The next one's going to be a little bit more difficult. So for example problem number 2, we have a 0.12 kilogram sample of iron at 98.9 degrees Celsius is being placed into a container of water that is 25 degrees Celsius. Both the water and the iron reach a final temperature of 30.1 degrees Celsius. What is the mass of the water inside the container? And again, they give us the specific heat values of the two substances. So this is a super special scenario. Since this is a closed system, we have water inside a container and we are adding a hot piece of iron to that water. The energy gained by the water equals the energy lost by the iron. That means the Q of the water equals the Q of the iron. So what I can do is actually take this equation or this relationship and take our Cm delta T's and set them equal to each other. So I'm going to clear off this slide just so I have more room to work in, and I'm going to rewrite this Q water equals Q iron. So the heat gained by the water is equal to the heat lost by the iron. And down the left-hand side, I'm going to write my C, M, and delta T for my water. And down this side, I'm going to write my C, M, and delta T for my iron. So C of water is 4,180. The mass is my unknown, and my delta T is 30.1 minus 25, which equals 6.1 degrees Celsius. Now over on this side, my C of my iron is 450, which is given right here. The mass of my iron is 0.12 kilograms, which is given in the first sentence. And my delta T of the iron is 25. And the delta T of my iron is 30.1 minus 98.9, which is a value of 68.8 degrees Celsius. Right now I'm not worried about the positive or negative aspect of that, because one of these Q values technically should be negative. This iron loses energy, so that's going to cancel the negative out, but right now I'm not super concerned. So I'm going to replace Q of water with Cm delta T, and I'm going to replace Q of iron with Cm delta T. This is just a substitution because I didn't give you a Q value, I did give you everything else. So I'm going to take 4,180 times M times 6.1 equals 450 times 0.12 times 68.8. I'm going to combine these numerical values to get 25,498 times M, and I'm going to combine all of this numerical value on this side, 3,715.2. Now mathematically, to rearrange, I'm going to divide by this 25,000 number, 498, and my mass is 0.145 kilograms of H2O. So in that container, I had 145 grams of water, or 0.145 kilograms of water, to allow that heat transfer to take place. So we're going to start with the first example problem, where we're just doing a few calculations and either multiplying or dividing to find our answer. And slowly I'm going to introduce more difficult problems like this one, where you have to keep in mind that the Q values have to be equal because it is a closed system. And if we put a hot piece of metal in water, or if we put an ice cube in some hot chocolate to cool it down, we can solve for an unknown based on that relationship. So I'll see you in class, and we're going to start with the simplified problems and work our way up. So I'll see you so we can work on this and answer any questions that you have.